Hi, my name is Victoria Paneva from the University of Bayreuth, and I will present HaptiRead, reading Braille as media haptic information. This was a joint effort with Sofia Seinfeld, Michael Krejci, and Jörg Müller. With HaptiRead, we evaluate the possibility of presenting Braille information as touchless stimulation using media haptic technology. HaptiRead delivers the information directly to the user's palm in an unobtrusive manner, which makes it particularly suitable for delivering short messages in public spaces, such as for reading the departure time of the next bus at a bus stop. There are several challenges that blind people face when engaging with interactive displays in public spaces. With audio displays, it is difficult to maintain personal privacy, as audio feedback is easily overheard by bystanders, and it can be perceived as obtrusive since it contributes to the environmental noisescape. Some interfaces, such as ATMs, feature a headphone plug. In this case, however, users need to remember to bring their headphones, and once they start the interaction, they might have more difficulty monitoring events in their immediate surroundings. Refreshable Braille displays consist of lines of actuated pins. They can be difficult to detect from a distance since the user has to touch them to know that they're there, and the physical contact with these interfaces could potentially cause hygiene problems. They contain moving parts which can become clogged by dirt and slower over time, and the information is limited to patterns of dots, which is suitable for text but not sufficient for content involving shapes, like for example data charts. Other methods and devices for reading Braille include Holy Braille, a system consisting of 6 vibrotactile motors and dampening elements that can be attached to mobile devices. V-Braille is a method for presenting Braille characters on a mobile phone, where the touchscreen is divided into 6 cells. When a cell representing a raised dot is touched, the phone vibrates. Then UB Braille is a wearable device consisting of 6 aluminum rings that transmit vibrotactile feedback. And lastly, Ludnitz et al. Investigated encoding text using a wearable haptic display in a hand, forearm, and 2 arms configuration. In this study, we use a meter haptic display that is composed of transducers that emit ultrasonic waves with phases such that one or several focus points are created in midair. The waves are modulated down to a lower frequency, which can be perceived by the human skin. So, how does midair haptics tackle some of the challenges with traditional Braille displays? The device includes a hand tracking sensor so that the haptics can be rendered directly on the palm up to a distance of 70 centimeters in midair. There is no contact between the user and the device, and only the user interacting with the interface at a given time receives the information. In addition, the midair haptic displays are highly programmable, featuring a wide range of haptic sensations that can be rendered. The contributions of our paper are: we test for the first time the use of midair haptics for reading Braille with blind participants. We demonstrate that it is possible to effectively distinguish between different Braille patterns rendered using midair haptics. And we present and evaluate 3 different haptic stimulation methods in a user study. We went through an extensive iterative design process. First, we brainstormed different ways how the Braille haptic stimulation could be delivered to the users, which are summarized in the table. Then we evaluated these methods in interviews with experts, in a pilot study with 6 and a preliminary study with 8 sighted participants. Through this process, we were able to identify the following 3 most promising methods: constant, where all points are simultaneously presented; point by point, where each point is individually presented; and row by row, where points of the same row are presented together. In the pilot tests, we also determined the best time spans for displaying the feedback for these methods. For example, in the point-by-point method, the best results were obtained when individual dots were displayed for 200 milliseconds with a 300 millisecond pause between subsequent dots. The user study consisted of a within-groups experimental design. The user study was conducted with 11 blind participants aged between 19 and 70. We opted for a simple experimental task that ensures high internal validity and experimental control. The task consisted of correctly identifying a pattern of dots limited to 4-cell Braille characters. The characters were presented with one of the 3 possible types of haptic stimulation: constant, point by point, and row by row in a randomized order. Before each experimental session, participants underwent a training session consisting of 4 trials. Then each experimental session consisted of 10 trials per method, so 30 in total. Well, when a participant recognized a pattern, they would state the corresponding character out loud. We did not give a time limit, but we did record the time to respond. We obtained an average accuracy of 81% for the constant, 88% for the point-by-point, and 75% for the row-by-row method. The mean time to identify a character was about 7 seconds for all of the methods. Using the Friedman test, no significant difference was found both in the accuracy and the mean time to respond between the 3 haptic stimulation methods. In the semi-structured interviews, participants expressed different preferences in terms of the haptic stimulation methods. Some said that the constant method felt closest to regular Braille, and others liked that with the row-by-row method they had an indication of how to orient their hand. The participants also mentioned tasks in their everyday lives where they could envision using HaptiRead, like for example to read a prescription at the doctor's office or to read a menu at the restaurant. This first validation study was conducted using a small subset of Braille characters limited to 4 cells individually presented. Further studies are required to validate the findings using a full 6-cell layout, as well as presenting the information in context, that is, in words and sentences. In conclusion, our results provide a first empirical validation of employing mid-air haptics for reading Braille. They show that it is possible to convey Braille as touchless haptic stimulation with all of the 3 proposed methods: constant, point by point, and row by row. The participants of the study responded quite favorably to the concept, but further testing and development is needed to explore the full potential of the technology for this particular application. Here are some further potential application scenarios of HaptiRead, like for example for reading the bank account balance at the ATM. Thank you so much for your attention, and for more information please check out our paper.